Have you ever dreamt of the ability to halt time itself, to preserve everything in that serene moment where nothing alters? Envision a world in which all motion ceases, light is restrained, and a profound stillness envelops the entirety. This is not merely a fanciful reverie, but a concept that physics has delved into over numerous decades, drawing us nearer to the absolute chill of the cosmos. Join me in exploring this journey, an inspiring narrative of human perseverance in confronting the enigmatic boundaries of nature, where science touches upon what once seemed utterly unattainable. Let us commence with a straightforward yet captivating notion. To freeze time, one must diminish the temperature to the lowest conceivable point, namely minus 273.15 degrees Celsius. At this juncture, atoms appear to cease all activity, as if drawing their final breath before descending into an eternal slumber. Light becomes imprisoned, no longer diffusing freely, and time seems to decelerate to a near standstill. This is absolute zero, a threshold that the universe appears to have delineated to challenge our endeavors. However, the path to approaching it has been far from straightforward. Humanity has expended over a century to reduce temperatures to levels merely a 10,000th of a billionth of a degree from absolute zero. And in those pivotal instances, scientists have unveiled secrets that have sent shivers through the entire field of physics. Picture the scene within the laboratory, where the biting cold permeates through layers of protective attire, and the machinery hums with a resonant whisper akin to the universe's own murmur. As temperatures plummet to extreme lows, liquid helium begins to behave as though it possesses a life of its own, ascending the walls of its container without any propelling force, utterly disregarding the gravitational pull of the Earth. It permeates through vessels like a silent apparition, leaving no trace behind. Scientists term this phenomenon superfluidity. It shatters the conventional rules of physics with which we are familiar, as if the cosmos is mocking our limited comprehension. Superfluidity exhibits no viscosity, signifying that it flows without encountering any resistance whatsoever, and it can climb the sides of a beaker, spilling over naturally, as though seeking liberation from the tangible realm. This discovery was not fortuitous. It was first documented in the 1930s by Piotr Kapitsa, who observed helium-4 at temperatures around minus 271 degrees Celsius. Since then, superfluidity has unlocked avenues for contemporary applications, such as cooling powerful magnets and medical magnetic resonance imaging machines, or even in experiments simulating the extreme conditions of cosmology, where we replicate the harsh environments of outer space. Recent research, as of 2026, has extended this to helium-3, a rarer isotope, where superfluid phases have been explored in quasi-two-dimensional confines, revealing chiral properties that could inform quantum technologies. Furthermore, advancements in sourcing helium-3 from extraterrestrial origins, such as lunar regolith, through initiatives like those by Blue Force and Interloon, promise to sustain quantum industry growth by addressing scarcity issues on Earth. In 2025, observations of superfluid phases in molecular hydrogen for the first time have broadened our understanding, drawing parallels with helium's behavior and potentially aiding in the study of ultra-cold atomic clusters. Yet the universe does not permit us to attain absolute zero with ease. The third law of thermodynamics, a foundational principle of physics, asserts that one may approach this point infinitely closely, but never truly reach it. It resembles pursuing the horizon. One pursues endlessly, yet it perpetually eludes grasp. The rationale resides in the quantum realm, where even at absolute zero, atoms do not remain entirely motionless. They vibrate subtly, as if programmed by the universe with an indelible code. This is zero-point energy, a fundamental form of energy that persists even when all appears tranquil. This energy arises from Heisenberg's uncertainty principle, wherein particles cannot possess precise position and velocity simultaneously, resulting in perpetual oscillation. Scientists such as Werner Heisenberg and subsequent quantum theorists have inferred that absent zero-point energy, the universe would collapse into utter immobility, but reality dictates otherwise. This is not merely abstract theory. It holds practical implications in fields like quantum electronics and even in elucidating the dark energy of the cosmos, where quantum fluctuations may contribute to its ongoing expansion.
Contemporary insights, drawn from theoretical physicists like Brian Greene, suggest that absolute zero's inaccessibility ties into the universe's dark energy, which constitutes approximately 70% of the cosmos and accelerates its expansion, potentially linking thermal limits to cosmic evolution. Continuing our odyssey, as humanity has lowered temperatures to levels thousands of times colder than the coldest spots in the universe, they have witnessed a phenomenon that stirs the soul: a collective amnesia among atoms. Thousands of atoms abruptly forget their individual identities, commencing to think and act as a singular entity. This is no science fiction. It transpired in 1995 when scientists Eric Cornell and Carl Wyman at the Joint Institute for Laboratory Astrophysics in Colorado, United States of America, cooled a cloud of rubidium atoms to near absolute zero. Abruptly, all atoms merged, not in congestion, but in genuine fusion, forming a solitary quantum wave.
They designated this the Bose-Einstein Condensate, the fifth state of matter in the universe, alongside solid, liquid, gas, and plasma. In this state, an atom may exist simultaneously in two distinct locations, fracturing the spatial boundaries we know. Imagine the scientists' exhilaration, the anticipation as they gazed at the screen, the steady drone of cooling apparatus like a cosmic symphony, and then the eruption of joy as the improbable became manifest. The Bose-Einstein Condensate is not solely a discovery. It heralds potential for quantum computing, where quantum bits process information at inconceivable speeds, or simulating black holes in laboratories to deepen cosmic comprehension. As of 2026, recent breakthroughs have included the creation of molecular Bose-Einstein condensates using microwaves at institutions like Columbia University, enabling long-lived dipolar states that open pathways for quantum simulation and novel materials research.
In 2025, studies on atomic Josephson contacts have replicated Shapiro steps in Bose-Einstein condensates, bridging superconductivity and superfluidity, while explorations of non-classical correlations in binary condensates and dissipative superfluidity in molecular forms have advanced applications in quantum sensors, precise medicine, and cybersecurity through enhanced quantum tunneling phenomena. How then did humanity uncover this forbidden realm? Over 2 centuries ago, in 1787, the French scientist Jacques Charles conducted experiments with gases, and subsequently Joseph Gay-Lussac in 1802 confirmed and disseminated the law. In a modest laboratory in Paris, with glass tubes glistening under candlelight, Gay-Lussac confined gases within tubes, heating and cooling them, meticulously noting volume changes. The outcome astonished him. Regardless of the gas type, a 1-degree reduction contracted the volume by a fixed amount. When graphed, the lines converged at minus 273 degrees, where gas volume seemingly vanished. Yet matter cannot disappear. This was merely the limit imposed by the universe. Later, with refined methods, the figure was established as minus 273.15 degrees Celsius. This marks the origin of absolute zero, a mathematical prison that humanity ceaselessly challenges. Undeterred, in the early 20th century, the race commenced. The Dutch physicist Heike Kamerlingh-Onnes devised the most potent cooling apparatus of his era. On a night in 1911, he reduced Mercury's temperature to minus 269 degrees Celsius and measured electrical resistance. The needle halted at zero. Initially deeming the equipment faulty, he soon recognized it as superconductivity. In superconductivity, electric current flows without loss, potentially enduring until the universe's end. If one places a magnet above a superconducting material, it levitates due to the Meissner effect, wherein magnetic fields are entirely expelled, creating a magnetic vacuum. This effect resembles an invisible hand providing support, and it has led to applications such as magnetic levitation trains, which travel at hundreds of kilometers per hour without friction. Recent intersections of superfluidity and superconductivity, as explored in 2025 studies on helium-3 extraction via entropy filters, highlight quantum filtration techniques that could enhance cryogenic technologies. A few years later, with helium at minus 271 degrees Celsius, it liquefies, but unlike any ordinary liquid. With zero viscosity, it ascends speaker walls, seeps through atomic gaps, as if possessing its own volition. Scientists initially doubted their observations, altering containers, yet helium persistently escaped.
This evokes profound mystery, as if the cosmos reveals secrets through these frigid droplets. How far has humanity progressed? In 2003, at the Massachusetts Institute of Technology, they cooled sodium to 1/50th of a thousandth of a degree above absolute zero. By 2021, the team at the University of Bremen in Germany dropped apparatus from a 120-meter tower, attaining 38 trillionths of a degree Kelvin, a figure with 10 zeros after the decimal. In those 2 seconds of freefall, the tower became the coldest locale in the universe. As of 2026, no newer records have surpassed this, per reports from organizations like the National Aeronautics and Space Administration and European scientific bodies, though experiments persist with aspirations of drawing even nearer. Does nature harbor such cold? Indeed, 5,000 light-years distant in the constellation Sagittarius lies the Boomerang Nebula. Clouds of gas from a dying star expand at 500,000 kilometers per hour, inducing a cooling effect akin to decompressing gas. The temperature is merely minus 272 degrees Celsius, 1 degree from absolute zero. Even the cosmic microwave background radiation, the Big Bang's echo, is warmer at minus 270 degrees Celsius. If one were cast into it, every cell would halt instantaneously, without time for a final thought or heartbeat. The body would freeze eternally, undecaying, as bacteria too would be sealed. Might this chill enable immortality? Theoretically, yes, halting the biological clock. Yet consciousness demands atomic motion. When they still, existence ceases. This paradox, eternity without perception. The universe trends toward this frigid terminus via entropy's increase, where heat flows from high to low until equilibrium. Stars burn out, black holes evaporate through Hawking radiation. In approximately 10 to the power of 100 years, all black holes vanish, ushering the universe into eternal invariance. This is heat death, where time loses meaning, leaving only infinite stillness. Insights from Stephen Hawking on black holes and entropy and Brian Greene on cosmological implications underscore how absolute zero relates to dark energy, potentially explaining accelerated expansion and the universe's fate. The cosmos locks space with light speed, time with absolute zero, confining life to isolated isles. Yet perhaps one day, a civilization will breach them. Until then, absolute zero reminds, the ultimate is not fire, but deadly silence, approaching each second. Cherish present warmth, for the warm era is a fleeting exception, while ice is the norm. From reputable sources such as Wikipedia, the National Institute of Standards and Technology, the Nobel Prize Organization, and posts on X from scientists like Carmela Padovich-Callahan, we observe that superfluid helium-3 is under investigation for fundamental experiments, while Bose-Einstein condensates are employed in quantum sensors and many body simulations. Inferences from Stephen Hawking regarding black holes and entropy, or from Brian Greene on cosmological significance, add that absolute zero pertains to dark energy, comprising 70.
Finally, we extend sincere gratitude to all the scientists mentioned, from Jacques Charles and Joseph Gay-Lussac with their pioneering gas experiments, to Heikki Kummerling-Annis for discovering superconductivity, Piotr Kapitsa for superfluidity, Eric Cornell and Carl Wieman for the Bose-Einstein Condensate, the team at the University of Bremen for the cold record, and research collectives at the Massachusetts Institute of Technology, the Joint Institute for Laboratory Astrophysics, along with figures like Werner Heisenberg, Stephen Hawking, and the global scientific community. We honor their enduring contributions, silent endeavors, and tireless dedication to human knowledge, which have illuminated the universe's dark corners and inspired future generations.